Hello, good morning. Welcome Prasant Misra. So Prasant Misra is a senior scientist at TCS Research, where he works on intelligent cyber physical system for smart and sustainable mobility. He is visiting faculty at Robert Bosch Centre for CPS, IISc Bangalore. He received his Ph.D. in computer science and engineering from UNSW Sydney and completed his doctoral from the Swedish Institute of Computer Science, Stockholm. So welcome, sir. So first of all, thank you for accepting our invitation.
Sure, thank you, Srinivas. Yeah. Glad to be here.
Yeah. So you can share your screen.
1 second. Is it visible now?
Yes, sir.
Okay, great. Let me get my pointer on. Okay. So, good morning, everyone. I extend my hearty thanks to BITS Pilani and AppCare Center for inviting me to give this talk. So today I'll be talking on this topic of how do you manage charging of electric fleets, but with a little bit of twist, wherein I will not only talk about how do you manage the charging aspects of vehicles, but also the discharging aspects of vehicles. And the reason being that if you can very smartly manage both the charging and discharging aspects of vehicles, there is an opportunity for doing some type of arbitrage that helps you to amortize or reduce the cost of operations. And this is going to be the main focus of my talk as to how do you manage both the charging and discharging aspects of EVs with arbitrage. Okay. Now this is a work that got accepted and published in AIML Systems last year. So it is the presentation from that conference. And this work was done in collaboration with Kshitij, Yogesh and Arun. In fact, Kshitij is the lead author of this work. And in fact, he presented this work in AIML Systems last year. So just to move ahead and set the context or the background for this talk, I'll just turn on my pointer. Yeah. So I think I think we all are very excited about electrification of the transport infrastructure. And if you look at it, the way the electrification journey is progressing, it is starting with the last mile. If you look at it, yes, there are multiple segments of transport electrification, but the last mile electrification is what is catching up pace and is catching up pace at a very fast pace. Purely because economics seem to be working in the favor to do business operations. Now, a couple of factors why EV adoption last mile is increasing. First and foremost, it leads to what we call as reduced OPEX, operational cost expenses, right? Of course, electric vehicles by their make and maintenance demand less cost compared to our traditional vehicles that currently use. And of course, the fuel prices, which in this case, electricity also is cheaper at this point of time compared to a gasoline powered vehicles, right? And if you look at the second aspect, sustainability benefits come from these vehicles, and sustainability benefits have a direct indirect impact on reduced OPEX, because if you look at a lot of governments across the world are giving what they call as sustainability scores, right? So if you have a good sustainability matrix, there are additional incentives that you actually get from the government for actually running the sustainable operations, right? The third point is that the transition from a non-EV ecosystem to EV ecosystem, the roadmap for electrification for last mile seems to be quite under control. And let me tell you why I'm making that point. So if you look at it, there are two sides that we have to balance when we look at the transition. One is we have to look at the demand side, right? Demand side here means that, hey, I need to do, let's say, I have to run a fleet of 30 vehicles and I have to do these many deliveries per route. So for me as an operator, I pretty much know what is the total distance each vehicle will travel. And if you look at it, the operations run in a manner that these vehicles run on those routes practically every day, right? The routes don't get changed unless there's a real need for it. So there is quite a good amount of predictability on the routes the vehicles will take and how many deliveries on that route they will do. And if you look at the standard e-commerce practices or last mile delivery practices, each trip length is around 80 to 100 kilometers, and the expected delivery is around 30 parcels or 30 packages on that route, right? So these are some numbers that I am quoting from how the last mile services, especially e-commerce, works currently. Okay. So what the point I'm making, the demand side, essentially in terms of how much energy I will need to drive my entire fleet, seems to be reasonably under control and predictable. I can predict it to a good amount of confidence. Now, from the supply side point of view, yes, supply side is that where do I get that energy to charge my fleet? Now, if I have to rely for that, I need to charge my vehicles, and for that I need to install chargers. Of course, if I don't have chargers installed, I have to rely on public charging, and again that brings uncertainty in the system. So to amortize that uncertainty, as an operator, I prefer to install these chargers in my depot or my warehouse so that I don't have to rely on any external third party to do the charging, right? So in that way, I can cut off the uncertainty in whether I'll find a charger or not, and if I arrive at that charging point, will I get the right amount of charge, the right speed or not, and so on and so forth, right? So, so the point here we are making is that there's better control over the fleet transition roadmap from ICEVs to EVs in the current scheme of things, especially for last mile deliveries. Okay, I think the fourth point is more interesting here. And by the way, a point to note is that in this business of e-commerce, the revenue opportunities are very sleek. Okay, because the cost of operations actually are quite high. So you need to really operate your fleet in a very, very efficient manner to make some revenue out of operations, some money out of operations, right? Now, so whatever as an operator I can do to actually make sure that that I can make that revenue or increase that band is always welcome. Now, in that regard, electric vehicles provide an option for arbitrage. Okay. Now, how does arbitrage come in the picture? Now, arbitrage here means basically I buy a commodity at a certain price and I sell the commodity at a certain price. So let's say I buy energy to charge my vehicles at, let's say, 5 rupees per kilowatt, right? And let's say there's an opportunity where the energy that is stored in my batteries, somebody is interested to buy that energy from me at, let's say, 10 rupees per kilowatt. So which means that I will actually make around 5 rupees per kilowatt if I sell energy from my vehicle, right? So that is arbitrage opportunity. So it would only make sense when my cost of buying energy is less than the cost of selling energy, right? And then only I can make some money out of it. So essentially, while saying is easy, operating in a real world context, especially in operation context, is difficult. However, the point here we are making is that there is an opportunity for it, which EVs do provide. Okay. So due to these 4 reasons or these 4 factors, electrification in the last mile has been catching up quite fast. Okay. Now, where does the problem lie? Okay. Now, so if you have to get into doing arbitrage, which means I want to buy and sell energy, I need to do bidirectional charging, right? I need to pull power from my energy resource or the grid and give it to my vehicle, and vice versa. I should be able to pull power from my vehicle and give it to a particular point which wants to buy energy from me, right? Now, doing that bidirectional charging management is non-trivial, and it is non-trivial even from the point that even if you have reasonable estimate of your energy demands, even if you have chargers that are deployed and are captively held in your location, in spite of that, bidirectional charging has multiple challenges. Okay. Now, if I have to break that challenge part, let me break that into supply side challenges and demand side challenges, right? Now, typically, if you look at the supply side challenges means essentially the charging infrastructure challenges, right? So when I, as an operator, I get into this bandwagon of electrification or transition, yes, I may want to buy X number of EVs, and for that, I may install, let's say, a wide number of chargers. Okay, typically, as per the Indian, if I am using the Indian charging standards, maybe one charger per 2 vehicles is a good ratio to maintain, right? So essentially, when I start my electrification journey, I plan for it that way. But if but the point here is that all these are heavy capital expenses, right? So it so happens that most of the time, as I add more and more vehicles to my fleet, there's a tendency to actually not aggressively ramp up the charging points in the same ratio as I have my vehicles, right? So basically, I somehow end up having fewer charging points than the EVs that I have. The best scenario would be like have one charging point per EV, but normally we have fewer charging points and more number of EVs, right? And it is purely done from upon the point that I want to make sure that my assets are well utilized, both my charging infrastructure assets as well as my electric vehicles for that matter, right? Second point is the grid in many cases is a bottleneck, especially for the Indian conditions. If we look at it, so the power line capacity from the grid to the last mile transformer to the load point of the depot, they could be capacity limitations. So essentially, let's say you have to charge a fleet of, let's say, 30 vehicles, 50 vehicles. The grid infrastructure may not be well conditioned to take that load. Okay, so there could be occasional blackouts. Third point is that if you want to do, let's say, arbitrage, and you want to do arbitrage with the energy markets. So essentially, we have this concept of energy markets, just like your commodity markets, where you trade bullion and other commodities. You can also trade energy. Yeah, so these markets are coming up. India also has a market. I think the markets are very heavily being utilized, basically in Nordic, in the European geography, especially Germany is one of the leaders in using energy markets. And again, in the energy markets, you have something called the day-ahead market and intraday market, just like you do in the commodity markets. Day-ahead market means you can place bids for this much quantum energy a day in advance, and intraday market means you can close the bids as close to 1 hour in advance, right? Short term. Okay. Now, if you recall, dealing with markets is very dynamic because there's a lot of volatility, uncertainty in the commodities availability and the prices. So you need to factor in that. Okay. So these are some of the challenges from the supply side point of view. And now from the demand side point of view, yes, I do have a good handle saying that, okay, I have 30 vehicles, each vehicle will do 80 to 100 kilometers. So from that, I can estimate that how much energy I required for my entire fleet of 30 vehicles. However, during the run, we should also account for other uncertainties. For example, let's say the vehicle is going on a typical route from A to B, and let's say that route is congested and you have to divert that onto a new route, take some, which means that you need to again plan for it, and that route will be longer than the regular route. So again, the EV may end up consuming more power and so on. So you have to somehow take care of the fact that even though you have a good handle on how much energy you need to run your fleet operations, there will be uncertainties and and you should prepare to deal with those uncertainties, right? So because of the uncertainties both in the supply side and the demand side, managing bidirectional charging operations is non-trivial, and that's the motivation for why we want to solve such a problem. Okay, now typically the objective of our work is to come up with an intelligent bidirectional charging management system with which we can arbitrage using a fleet of last mile EVs so that we can reduce the fleet charging cost while meeting the operation constraints. So this is what our objective is and what we want to do. We want to come up with a bidirectional charging management system with arbitrage. And the goal is to reduce the fleet cost charging cost for the fleet, but make sure that our business operations don't get hampered due to these arbitrage operations. Okay. Now, what are the challenges for coming up with such a mechanism? Now, we have put down 5 such challenges. The first challenge is that we have limited charging flexibility. Now, what do we mean by that? So essentially, if we look at fleet operations, they run on tight schedules. So example, let's say I have to run 2 shifts. Let's say the first shift starts at 6 in the morning and ends at, let's say, 1 in the noon, and then so within which the vehicle has to go into the city, do the deliveries, come back to depot, and then the next shift would start maybe after half an hour or 1 hour break. Let's say from 2 p.m. again it starts, and maybe the shift ends at like 8 or 9 p.m. right? So if you look at it, and then of course overnight it stays in depot. So what the point we're making is that between shifts, there is limited charging flexibility in the sense that you have to make sure that if you are taking any charging decisions, you have to align with those windows within which the vehicle is in the depot, and we have to make sure that the vehicles actually are ready with the right amount of charge when they are supposed to go on their scheduled deliveries, and there cannot be any delay in that. Okay. Second thing is there is limited trading flexibility due to trading flexibility depending upon are you playing in are you operating in a day-ahead market or intraday market. So essentially, if you look at it, so essentially you may have committed, you may want to buy a certain quantum of energy in the day-ahead market, right? And then you may want to also take advantage of the volatility of the intraday market to make some more revenue of it. But then the day-ahead commitments that have been committed, they need to prioritize the intraday commitments. So essentially, it's not like you get a better price in the intraday market. You may say that, okay, I am not willing to buy energy from the day-ahead market because the commitments have already been done, right? So again, there is limited trading flexibility wherein you have to honor the commitments that have already been done while seeing any new opportunities that may come in the future. Third point is that the electricity price volatility is there in the sense that the volatility in both the markets, whether it's day-ahead and intraday, they have different dynamicities, right? Of course, the volatility in the intraday market is much greater than the day-ahead market, but nevertheless, they are fluctuating. And then fourth point is that when we are doing this, when you're coming up with a planning solution for this, we have to plan for errors and deviations so that any errors in the planning process will creep into subsystems. So we have to make sure that making sure that the errors that come in stage 1 do not pass on to the greatest extent to stage 2. Those types of propagation errors have to be taken care of. And finally, I think this is a very important point. I think it's a difficult problem to solve computationally, especially at very large scale. So if you are trying to come up with such a plan for a small number of vehicles, let's say 10, 15, 20 vehicles, it is fine. But let's say you have a fleet of 1,000 vehicles or 500 vehicles, right? So how do you come up with such a system at scale is where it is computationally extremely hard to come up with a proper solution, right? So these are the motivations as to why we want to solve this problem. And what are the challenges within which we have to operate? Okay. So moving ahead, I think this is basically the operation problem. Okay. So this is the fleet manager sitting here, right, or the operations manager. And as I mentioned, you have a fleet of vehicles. You have some few captive chargers. There's a departure schedule for the vehicles. There's a delivery route for these vehicles, and you are trying to buy and sell energy in the energy markets, both intraday and intraday, right? So these are some of the givens to you, and you need to obtain certain things and the constraints within which you have to operate. So this is basically the larger operation questions that we want to solve here. Now let me break that down. So what is the solution that we have come up with? So the solution that we have come up with is actually twofold. One is we come up with a day-ahead planner for charging, and we also have a intraday planner for arbitrage. So what we have done is that we do not use both the markets, which means we do not use the day-ahead and the intraday market for doing charging and arbitrage as is. Okay, so we have somehow divided roles. We say that we will do charging only in the day-ahead market. So essentially, whatever energy I need to buy from the market for charging, I will use the day-ahead market for that. Whereas if I have to do arbitrage, which means I want to sell and buy energy, that is something I'll do in the intraday market. Now, why is this model we believe is good? Because somehow it's we have a very nicely decoupled operation model, wherein of course you meet your charging needs from the day-ahead market, which means that your regular business operations don't get impacted. But yes, if you have an aspiration to make some more revenue through arbitrage, you can nevertheless do it in the intraday markets. Okay, so essentially, as I said, it's completely out of the operator as to how risk averse he wants to be. If he typically doesn't want to take any risk, he can simply work with the day-ahead markets and get the right amount of energy for charging. However, if he wants to make a bit more money by taking a bit more risk, he can then actually work around with the intraday market, right? And for both these planners, the day-ahead planner and the intraday planner, we have two different types of techniques. So we have come up with a graph representation based learning technique for the day-ahead planning, and priority order based greedy heuristic for the intraday planning, right? So this is how the overall solution looks like. Okay. So essentially, as I said, we have the day-ahead planner, and for that we have designed a learning agent. And I'll run you through how we have built that learning agent using the decision control techniques. And of course, and we can also and when we have to come up with intraday planner, a lot of inputs from the day-ahead planner are fed into the intraday planner, and it also has to capture some more stage information to come up with that day-ahead planning technique. Okay. So these are these are some of the system parameters. So we have parameters for the charging stations. We have different types of parameters for the vehicle itself, different parameters to capture the dynamics of the energy market, and some of the decision variables that we typically. So of course, a lot of the decision variables are consumed by the system, but the final decision variables that we want to come up with is essentially which vehicle should be assigned to which charger and at what charging rate or at what discharging rate, right? So that's the final decision that we want to come up with. Which vehicle, which charger, what should the charging rate be, or what should the discharging rate be? Okay, and for how long? Okay, so that's the decision we want to come up with, and we have tried to model this problem. So essentially, this is the end-to-end operation problem. So as I said, we have divided this solution in two parts: the day-ahead planning module and the intraday planning module. And we first designed this automation. We tried to model this operation problem and solve it using mixed integer linear programming, nonlinear programming techniques. So we have built MI-NLP. In fact, I have to correct this for the day-ahead charge planning and also intraday charge planning. So if you look at it, we take inputs from the input parameters for the market conditions, the vehicle, the charger, and of course there are certain outputs it gives. Some of these outputs are again, these are we model them decision variables which are again fed back into the planner to again help with the decision making, while some are the final output. For example, what should a charging rate, so essentially which vehicle should be assigned to which charger and what charging rate is something that comes out from there, right? And that is again fed as input to the intraday charge discharge planner. And of course, for that again we need to give additional matrix on markets, vehicles, chargers, and finally the output that I get essentially for the intraday market, which vehicle again should be assigned to which charger, and what should it be charging or discharging, and if it is charging discharging, what should the charging or discharging rate should be. Okay. So the objective of the first planner is to minimize the charging cost of all vehicles in the fleet using electricity prices from the day-ahead market. So the first planner, which is the day-ahead planner, as I mentioned, you want to use it solely for charging purposes, and the aim of that particular stage is to minimize the cost of charging of the entire fleet. Okay. However, the objective of the stage 2 is slightly different, wherein here we want to maximize revenue through energy arbitrage using intraday markets, which means that when I want to enter into energy arbitrage, I want to minimize the cost of energy buy through charging, and I want to maximize the cost of energy sale through discharging, right? So I want to maximize my sale of energy, and I want to minimize the buy of energy, right? So then only I can really make some money out of it, right? So that's the objective of the second stage. Now, while this is, and in fact, we have a very detailed formulation for it, which I will take you through in a while. But to give you how complicated this problem is, so as I was mentioning, solving such a problem at scale is the challenge. For example, at each decision time step, I have to come up with these many decision variables. Essentially, I have to I into j into k. And what is I? I is essentially the number of vehicles, j is the number of chargers, and k is the number of charging rates, right? So if you have a fleet of 5 vehicles, let's say you have three charging stations, and let's say the charging station supports 16 charging rates. Let's say it can go for all the way from 1 ampere to 16 amperes at a step of 1 ampere each. So you have like 16 charging rates, right? And you want to do it for t is equal to 96 steps, essentially for the entire day, right? So you will, for such a small problem dimension, right? We will have to end up calculating around excess of 5,700 decision variables, right? For such a small problem. So you can imagine if you have a larger fleet, let's say of 100 vehicles and let's say 50 chargers, you can imagine how the complexity of the problem grows exponentially, right? And that's where we need some alternate approaches that can actually give us solutions at scale. Okay. The next few slides will take you to the operation problem. I'll be a bit quick in this because this may not of course these details are in the paper, but I'll just try to cover it for the purpose of completeness. As I mentioned, the objective in stage 1 or routine 1 is to minimize the cost of charging of all vehicles using electricity prices from the day-ahead market. Now, so essentially, if you look at it, P is the price from the day-ahead market, and this is the so this is essentially the RK is the number are the discrete charging rates, and essentially this would mean small r here is essentially, let me check, small r essentially tells us if a particular vehicle is charging at a certain at the JS charger and at the kth charging rate, right? So essentially that's how I compute how much power am I drawing from there. Okay, and there is a penalty term also that I want to minimize. The penalty term tries to capture the fact that if I am not able to meet the energy demand by the deposit deadline, the system will incur a penalty. And the penalty also given if the vehicle keeps on switching chargers, which is not practical. So let's say you are charging, if you look at how the optimizer works, so at every decision time step, across this decision horizon, it may switch chargers. Okay, it may start charging at charger 1, but in the next decision time it may again flip onto charger 2 or 3, right? And that's typically, as we understand, it's not practical if a vehicle is charging at a particular charging station. So you need to you have to penalize the solver of the optimizer to make sure that a behavior that it doesn't pick up that behavior, right? And then it's conditioned multiple constraints. So example, the first constraint is that a particular vehicle cannot charge at more than one charger simultaneously, right? So this is a constraint that tries to ensure that. The next constraint ensures that the state of charge of the vehicle does not exceed the battery capacity. So let's say I have a battery of 25 kilowatt hour. At any point of time, so essentially when at the end of the planning horizon, my SOC cannot be more than what the battery capacity is. Essentially, I cannot have 30 kilowatt hour in a 25 kilowatt hour battery. Essentially, right. Then the other constraints are like the vehicle cannot charge when it's not in depot. So let's say the vehicle is on the go. Of course, since not in the depot, it cannot charge, and the vehicle can only charge at compatible chargers. Of course, there's a question of compatibility comes in because you may have charging points, but do they have the compatible charging interface to interface with the vehicle charging interface is a question to ask here. So essentially, we want to make sure that it happens only at compatible points. And when we're choosing the charging rate, we want to make sure that the charging rates are within the defined charging rates of the charger. For example, if the charger supports a charging rate from 1 amp to 16 amp at a step of let's say 1 amp each, it has to obey the physical limitations of that charging station, and it cannot choose any charging rate that it decides essentially. For at every decision at any given time, only one charging rate can be chosen for a charger. Of course, at the next time instant, the charging rate can again get revised, but at that particular time instant, one charging rate can only be assigned to a charger for that vehicle. The other constraints, so this is a constraint that tries to somehow track the SOC from one time step to the next time step. And then there's a constraint that says that you cannot use a charger when it is not available. There's another constraint that that typically it's not a constraint, but it's initialized. Essentially, when we start the entire process, the vehicles need to initialize with some starting SOC essentially, right? Because let's say the vehicle is in the depot, and let's say there is some 10% charge in the vehicle, so you cannot start the entire solving process assuming that there is no charge. So you have to initialize with the charges that the vehicle holds at that point of time. And there's another, so again we need to set this parameter delta, and which typically tells us how many switches between the different charging points happens for a vehicle, and we want to minimize that. So this is how we calculate the account for the number of vehicle shifts over there. Now the second routine 2, as I mentioned, we want to maximize the revenue through energy arbitrage using intraday markets, which means that we want to minimize the cost of energy buy through charging and maximize the cost of energy sale through discharging, right? So again, I think most of the constraints that we went through, most of the constraints hold the same. It's just that they have to be conditioned on intraday dynamics. For example, when we are in intraday period, let's say a particular decision has been taken in the day-ahead schedule. So essentially, in my intraday planner, I cannot override those decisions because those decisions were already taken for the day ahead schedule for that matter, right? So those have to be respected. Similarly, SOC requirements have to be respected. Again, the vehicle availability and vehicle charge compatibility has to be respected. And the charging discharging rates have to be respected. Just hold on 1 second. Just hold on. Yeah. I'm so sorry. And then I think this is a constraint that says that basically essentially at any point in time, at any given time, only either the vehicle is in charge or discharge. It cannot do both of them at the same time, right? So this is a constraint that tries to ensure that. And I think, yeah, other constraints are similar to what we discussed in routine 1, but they are specific to the intraday conditions. Okay. So you can look at it. So essentially, yeah, this was the summary slide that somehow summarized how the end-to-end automation problem works. There are two routines. The output from the first routine is fed to the input of the second routine, and then I think once you solve it, the second routine, you get the entire solution for both for the day ahead as well as intraday. And both the routines have their own objectives. And what I just showed is that if I showed you how the operation problem is formulated, what is the objective in each routine, and what are the constraints in each routine. And as you can make out, and I was making the point that you have to calculate these many decision variables for even a small problem size, and you can now make out that why it is such a complicated problem when you look at the number of steps you have to go through to come up with the optimal solution, essentially. So to overcome that, what we have done is we have come up for the day ahead part of it. We have come up with a learning agent model, okay, for charging. And of course, as I mentioned, the charging, the planning decision here is essentially which vehicle is assigned to which charger, at what charging rate, and for how long should it charge. So that's the charging decision that I want to come up with, right? So what we have done is that so this is how the entire learning model end-to-end looks like, essentially. So the first stage is that we try to we try to prepare the model with certain with certain things. The first is that we have something what we call as the vehicle state. Okay, so let's say we account for all the vehicles in the system and typically different aspects of vehicles in terms of what's the state of charge of each vehicle and so on and so forth. And then we have something called operation state. So operation state is a mapping between a particular charger and the charging rate. So let's say charger 1 supports 16 different charging levels. So essentially, I will typically have all those enumerations, what I call as charging operation states over here. Okay. Now, so if I then I can view that now as a graph structure. So essentially, what can happen is that let's say charger C1 supports charging rates from R1 to RK. Okay, which means that this vehicle V1 can be assigned to charging station C1 at rate R1. It can also be assigned to charging station C1 with rate R2, and so on for other rates that it supports. Similarly, vehicle V2 can also be assigned to charging station C1 and other charging stations C2, R1, so on so. So if you look at it, it is like a bipartite graph in some way, right? Now the question to ask is that what is the optimal combination, in the sense that which vehicle should be assigned to which operation. And operation by here I mean which charger and what charging rate. Okay. So if you look at it, there is some form of a structure here, and I try to capture that structure using the graph neural network. Okay. So there are two stages of the graph neural network. The first stage is what we call as the vehicle node embedding. The second stage is the operation node embedding. So of course the paper will tell you the math that goes behind it, but from a simple illustration point of view, which is quite intuitive to understand from this figure. So when I say vehicle node embedding, what I do is that I try to embed the information from the vehicles to this to the operation state here. Okay, and embedding here means all the aspects for that vehicle, all aspects for that operation, and also the edge attributes here. Okay, so I encode that. So and this I do for all the way from left hand side to the right hand side. And in the second stage, I do the same thing now from an operation node point of view. I say that, okay, now let me, I have in stage 1, I encoded from this side to that side. Okay, I looked at from perspective of the vehicle and said that how do I encode this, embed the information from the vehicle to the operation node. In the second stage, I look it from this perspective. I said that, okay, now given that I have the operation node, how do I now encode or embed information from right to left, in the sense that, okay, which all vehicles are incident on me, so I encode all the information, and from there I have to come, I have to somehow come up with so when I do this exercise, some of the things, some of the relationships between the vehicle to the operation state may not be feasible. Okay, so those entries get knocked off, and I typically then come up with basically these feasible actions, saying that this vehicle can be assigned to this charging station and this charging rate. So I will have a couple of these feasible actions. So then I feed it to a policy network, which typically then weighs those actions, saying that, okay, action 1 has a weight of this one, action 2 has a weight of this to this much. And what I do is that I then choose the action that gives me the highest weightage. Okay, and that action is what I then go and update in the environment, saying that now action, recall, action for me is that which vehicle should be assigned to which charger to which charging rate, right? At what charging slot. So that typically comes out as output from this policy network now, and that is something I update the environment, and then I get a reward for taking the action. And based on the reward, I try to then modulate my decisions, okay, and adjust my decisions. Okay, now what is the benefit of this model? Now, the reason for using a graph representation is the following. So if you look at it, what you see here is essentially a varying size heterogeneous graph, right? Why varying size? Because let's say at any time instant, so the number of vehicles and the number of charging stations and charging is available keeps on varying at every time instant. So let's say at time instant T1, you had, let's say, 10 vehicles, and there were let's say 5 chargers, and each charger was supporting 2 charging rates. So you had like 5 to 10 combinations, and you had 10 vehicles. So that was at state at time instant T1. And let's say there is some assignment that has happened. So next time, vehicles that have been assigned. So next time we have to look at vehicles that are yet not assigned, right? So again, the graph structure will vary. So you don't have fixed graph structure. So you need a representation that is able to deal with such varying graph structures, and this is where graph neural networks helps to give us an edge. And in spite of the dynamicity of these mappings, we are able to come up with a fixed dimensional embedding at the end of the exercise. So the benefit that we get is that irrespective of the graph dimensions, which may vary at each time instant, we always have a fixed dimensional embedding for that, and that typically helps us to solve the problem in an easier manner. Okay. Okay, let me skip over this. I have just 5-10 minutes more. So essentially, this is how the the state graph features are, operation node features are, edge features, and then what action I take and what's the reward. Okay. Again, this is the learning architecture for it. As you can see here, this is the training results. So if you look at the reward, typically I think till around 60 episodes, the agent keeps learning, and after that it somehow stabilizes. Yeah. So this was that. So the learning model, learning agent model was for the day ahead, and for the intraday we have the we have designed heuristics. As a heuristic. Why heuristic? Because intraday decisions have to happen in very short time horizon. So we don't have too much time in hand to compute. So we have come with a easily usable heuristics. So heuristic is based on a priority index. So essentially what we do is that we try to calculate the urgency of a vehicle to charge. We calculate the cost of charging and discharging. We try to also look at the difference between what is the forecasted intraday electricity prices versus our current running average. And then the final thing is that should be which charging rate and discharging rate will maximize my utility over here, right? So I come up with a priority function based on all these 4 different levels of priority, and based on that I come up with a planner saying that which vehicle should be assigned to which charger and at what charging rate. Okay. So quickly moving on to some results here. So just to recap here, I'm going backward again. So what we have discussed is that we discussed the day ahead planner, and we also discussed intraday planner. And for the day-ahead planner, what I discussed is a learning agent that is essentially a graph network with a two-stage encoding. And for the intraday planner, we have come up with a priority order-based heuristic. And mind you, both these planners are different objectives. The day-ahead planner is solely for making sure that we're able to charge the entire fleet, while the intraday planner is used for arbitrage operations, wherein I engage into selling and buying energy in this stage. Okay. Okay, so just to go on some results. So this is the evaluation studies from the day-ahead charging. So let's say your operating system where there is no intraday market with you, you just have the day-ahead market and you have come up with the day-ahead planners. Okay, so LA3 is our technique, and we have compared that with, of course, the baseline MILP, which is this one, and we also have compared that with the greedy heuristic and two other learning agent methodologies that were discussed in literature in the past. So what you see in terms of solution speed, the greedy, of course, I think the MILP gives the best cost, the least cost here, right, compared to any other technique. But we are able to go up till 5 vehicles and 4 chargers, right? Beyond that, if I increase the scale the problem for more than 5 vehicles, I don't get a solution, right? So that's why I put NA here. However, I think other techniques are able to scale. And in terms of solution speed, the greedy heuristic is the fastest. But in terms of the solution accuracy, our technique essentially gives us the best accuracy. And if you look at it, given that it's a day-ahead planner, which means that you have 24 hours with you to actually come up with the planner, the solutioning time is not that bad. For example, of course, we don't get the solution in seconds, but we do get the solution in a couple of minutes. For example, if you have a fleet size of 25 vehicles, we can give you a solution anytime, anywhere between 2 to 10 minutes. If you have a fleet size of 50 vehicles and different combination charges, we can give the solution between anywhere between 4 to 24 minutes, and so on and so forth. And purely because, and this is reasonable because you have around 24 hours time in hand to actually come up with the planning decision here. If it had to be real time-ish, then of course these numbers would not make sense. But given that you are doing it a priori, you have time in hand, you can work with this essentially, because at large scale, the solution accuracy is much better than what typical is reported currently till now. Now, this is a table wherein we compare the results from both the day-ahead and intraday planner. Okay, so what we have done is that, now just be mindful what I mentioned here. So essentially, see D means day-ahead and _I means intraday. Okay, so here I've combined the MINLP day-ahead with the MINLP intraday. Okay, and here I have combined the greedy heuristic day-ahead with the greedy heuristic intraday. Whereas for all the other three, which including ours, for the day-ahead we have the learning agent model, and for the intraday we have the greedy heuristic. Okay, so this is the combination we have done. Okay, so what I report here is essentially, if you are doing arbitrage, which means that if you are doing both day-ahead and intraday together, as opposed to just doing day-ahead, what is the benefit or the cost savings you get? So, and this blue part captures that cost savings. So it says that if you combined the day-ahead intraday planners, you would get around 20% more saving compared to just using a day-ahead planner for a fleet size of for this type of a fleet configuration. Okay. So if you look at it across all different types of configurations, whether it's 25 vehicle fleet, 50 vehicle fleet, 100 vehicle, 250 vehicle fleet, and different numbers of chargers over there, you can see that if you are using a combination of day-ahead plus intraday planning, which means that you are doing not only charging but also arbitrage, you can get somewhere between 17 to 22% on average savings compared to just using a day-ahead planner, right? And that's the benefit that arbitrage brings in. Okay, so and the point that comes another interesting point or observation that we note here is that as the fleet size increases, if you have more vehicles in the fleet, the savings that you also encounter also goes up, and it only makes sense because you have more energy as a whole at your disposal to do such an arbitrage operations compared to a smaller fleet size. So essentially, so that's why if you have a fleet of fewer vehicles, let's say less than 50, your savings as per the current analysis doesn't cross 17%. But if you have a larger fleet size, let's say you have a fleet of more than 100 vehicles, on average you can actually save more, above 20%. Okay, so this is the conclusion that we come up with. So with this, I'll come to the final slide. So just to summarize what I presented. So we presented a model for bidirectional charging and arbitrage using electric vehicles. We formulated the optimization problem as a two-stage optimization approach. And we showed that classical approaches don't scale that well. And that's where we have come up with a combination of a day-ahead planner that uses sequential decision making in conjunction with intraday planner that uses greedy heuristic. And we evaluate our joint day-ahead intraday planner on specific data sets. And we are able to show that if you are show that the combined planning with arbitrage gives around 70 to 20% cost reduction over cases where we don't do arbitrage. So that's the key takeaway or the key observation or finding that we come up from this particular study. Okay. So with this, I've come to the end of my talk. So I will pause here. I am not sure if there are any questions, but if somebody would like to pose some questions, very happy to answer. Yes, so thank you, Srinivas, thank you, AppCare, thank you, Bitlani, for giving this opportunity. And I'm open for questions now.
Is there any questions?
So I'll just pause in the slide because this is more or less the operational question that we are trying to solve. So I just want you to have a picture of the slide so that you can at least take back that what we are trying to solve and what was given to us, what we wanted to obtain, what are the constraints and what approach we have currently come up with.
Okay, sir. Thanks a lot for accepting the invitation once more. And it was a good presentation.
Sure. Thank you, Srinivas. Thank you for your time and thanks for listening. Yes. Thank you, Snehanshu, as well. Nice connecting with you.
Thank you, sir. Okay.
Yeah, thanks, Prashant. Nice talk.
Thank you, Snehanshu. Yeah, thank you.
Right.
Maybe I think if I get a future opportunity, maybe we'll do that in person because this is a little bit more analytical.
Yeah.
Require a bit more support rather than online. But I hope I was able to convey the main message.
I will arrange it. Okay.
Yes.
Okay, chalo, I'll call you sometime to